There's an intriguing apparatus that appears in numerous videos aimed at visualizing the Pythagorean theorem. It consists of a rotatable wheel holding three rectangular containers that are built on the sides of a right triangle. The idea is that when the wheel is turned, liquid flows out of the two filled smaller containers, perfectly filling the empty larger one, and vice versa, thereby illustrating the Pythagorean relationship. As creative and interesting as this device is, something about it never really sat right with me. Named after Pythagoras of Samos, the Pythagorean theorem states that for any right triangle with side lengths a, b, and c, where c is the hypotenuse, the areas of the squares built on the sides a and b add up to the area of the square on side c. It is this relationship that gives us the familiar a² plus b² equals c² equation. So, the Pythagorean theorem is based on area, a two-dimensional measurement. But the rotating wheel contraption shows a relationship between volumes of liquid, and volume is a three-dimensional measurement. Although the water wheel ultimately misses the mark when it comes to accurately depicting the Pythagorean theorem, it serves as a foundation for some great discussion and raises some stimulating questions. In particular, does a 3D version of the Pythagorean theorem exist? The water wheel provides us with some very convincing evidence that it does. The reason it works is because the three rectangular prism containers all have the same thickness. We can prove it works algebraically by letting d represent the thickness of the rectangular containers and starting with our Pythagorean theorem equation a² plus b² equals c², which we know is true. Multiplying both sides of this equation by d and expanding gives a²d plus b²d equals c²d. When we realize that each term in this equation represents the volume of a rectangular prism, we see that the Pythagorean relationship will indeed always hold when using volumes of equally thick rectangular prisms instead of areas of squares. That is, the volume of a rectangular prism constructed on the triangle's hypotenuse will always be equal to the sum of the volumes of the rectangular prisms built on the other two sides. Perhaps it would be more interesting to consider whether this relationship holds for cubes built on the sides of a right triangle. In other words, do the volumes of the two cubes constructed on the smaller sides of a right triangle add to the volume of the cube built off the hypotenuse? Does a³ plus b³ equal c³? It turns out for a right triangle this can never happen. Let's see why. For a right triangle with side lengths a, b, and c, where c is the hypotenuse, we know by the Pythagorean theorem that a² plus b² equals c², or a² equals c² minus b². We want to know if it's possible for a³ plus b³ to equal c³. Let's assume that it is possible and see what happens. Rewriting a³ as a² times a, we can substitute a² with c² minus b². From here, we can subtract b³ from both sides of the equation and divide both sides by c² minus b². Now let's factor the numerator of the expression on the right side as a difference of cubes and the denominator as a difference of squares, and then simplify. Finally, we can common factor the first two terms of the numerator, split the fraction up, and simplify. Our result is that a is equal to c plus b² over c plus b. But wait a minute. This equation implies that a is greater than c by exactly b² over c plus b. But a can't be greater than c because c is the hypotenuse length. Therefore, our assumption that a³ plus b³ could equal c³ is incorrect. It cannot actually happen. What if we dropped the restriction that the triangle is a right triangle? Could a³ plus b³ equal c³ for non-right triangles? Well, Fermat's last theorem guarantees us that the equation a³ plus b³ equals c³ has no solutions where a, b, and c are all integers. But if we open the door to solutions involving non-integers, we see that there are infinitely many possibilities. All we have to do is choose values for a and b and solve for c. If we then build a triangle with side lengths a, b, and c, it won't be a right triangle, but the volumes of the cubes built off sides A and B will add to the volume of the cube on side C. One last detail. Perhaps you're thinking, how do we know that we can actually make a triangle using side lengths found like this? After all, there's no guarantee that any 3 line segments will be able to form a triangle. Well, we can construct a triangle with 3 given side lengths as long as the sum of every pair of side lengths is greater than the other side length. That is, A plus B is greater than C, B plus C is greater than A, and A plus C is greater than B. Keeping in mind that A, B, and C are positive values, we can quickly show that as long as A cubed plus B cubed equals C cubed, this condition will be met. To show that A plus B is greater than C, we start by expanding the cube of A plus B, which gives A cubed plus 3A squared B plus 3AB squared plus B cubed. Since A and B are positive values, 3A squared B and 3AB squared are also positive, which means that our left side must be greater than A cubed plus B cubed. And A cubed plus B cubed is C cubed. From here we can conclude that A plus B must be greater than C. To show that B plus C is greater than A, let's start with the fact that C cubed equals A cubed plus B cubed, and therefore C cubed minus B cubed equals A cubed. This equation implies that C cubed is greater than A cubed, and therefore C cubed plus B cubed must also be greater than A cubed. From here, we reuse a property that we just demonstrated. C plus B all cubed is greater than C cubed plus B cubed, and must therefore also be greater than A cubed. At last, we can conclude that C plus B is greater than A, or as originally stated, B plus C is greater than A. Finally, we can repeat this argument to show that A plus C is greater than B, and thus a triangle can indeed be formed using any solution of the equation A cubed plus B cubed equals C cubed for side lengths.